Starting recording now, and let's begin. My name is Kuba Glazek. I'm one of the NCADE methodology experts, and today I'll be doing part one of a walkthrough through a statistical analysis of a data set. And I'm recording this presentation so that if anyone is watching it not live, that they will be up to speed for part two. The reason being that for this hour today, which is part one, I want to cover the general steps in this walkthrough. And then tomorrow, I want to go through all the technical details that go along with those general steps. So this recording should be useful for those who are not with us live, who still want to take advantage of part two. And so basically to begin, the point of this data set that I was able to find online is that we can start to look at the relationships between physical health symptoms, mental health symptoms, and stressful life events, and their relationship to visiting a health professional. So what you can imagine sort of is conducting a lit review and collecting some data, trying to predict whether or not folks will visit a health professional on the basis of their physical, mental health, and any stressful life events that they experience. So in the sort of big picture sense, we can imagine that visiting a therapist might negatively impact the rate of self-injurious behavior or depression or suicide. This data set doesn't have that information, but in any case, we can see if these variables play a role in the number of times that people actually do go see a health professional. So this data set is available at the website that you see on the screen there. So if you want to download that, please feel free, and you can play around with it at your leisure. But moving on from here, since this is the analysis we're working on, it's almost independent of the process, but it's something that I think will be near and dear to a lot of folks who are tuning in. So the general steps with any kind of analysis, quantitative analysis, is to first enter your data. And then second, to screen the data, which is to say that you would first run a regression to obtain diagnostic values. And what I didn't actually mention on the previous slide is that this analysis contains all continuous, also called quantitative, also called ratio variables. And the importance of that is that the type of variables that you have will dictate the type of analysis that you're going to conduct. And in my experience at the Chicago School, a lot of students rely on these types of continuous variables. So that's what I'm going to focus on. So anyway, when you're screening data with a multiple regression, you would first conduct a sort of preliminary regression run to obtain a number of diagnostic variables that would help you then understand how well your model actually predicts the outcome, in this case, visiting a mental health professional. So one of the first things that you would do is obviously get these data, and then you would look at them and do remediation on any violations of statistical assumptions, on any overly influential cases, and then you would conduct a second regression which would allow you to obtain the same diagnostic variables, but now the values would be different on the basis of having applied some of these remediations. So that's really kind of the heart of the matter, is that you would gain knowledge of what your data look like in order to be able to then make sure that the inferences that you're making are actually valid. And then that's the last piece of the puzzle, is to conduct a final analysis on a model that you know is not succumbing to any weaknesses of the data that might be inherent in the raw data themselves, without addressing all the violations and influential cases. So Again, the very first step is entering data. So I'm going to go into the technical details of this process tomorrow, like I said at the outset. But what you can generally see from this particular screenshot is a couple of different things. The first of which is that we're looking at just your standard kind of layout of SPSS, and the other thing is that I want to draw your attention to this box down here in the bottom left, which highlights the difference between data view and variable view. In variable view, so currently this screenshot here is in data view, but in variable view, you can tell SPSS what kind of variables you have. And it calls ratio or continuous variables scale variables. So you can tell it that that's the kind of data that you're inputting. You have the ability to also input ordinal variables, which is something along the lines of a variable that has a few different levels, that one is higher or greater than the other, if you will, such as, let's say, grade level. So first grade, second grade, third grade, fourth grade. Those are obviously, one is higher than the other. And then you also have nominal variables, which are simply categories that do not have an order. So something like eye color. You can't really say that, you know, blue is somehow greater than green or brown or what have you. So there's all kinds of different variables that SPSS can handle, but you have to tell it what kinds of variables those are, and you do that through clicking on that variable view tab at the bottom. So it's a sort of, it's a different side of SPSS as opposed to the data view, which we're seeing here, where each column is one variable. So in our case here, we have 4 different variables, one of which is the number of doctor visits, right? I've sort of introduced that. Then we've got physical health symptoms, and we've got mental health symptoms, and we've got the number of stressful events that a person has experienced overall. And next, it's important to note that each row, so row number 1, row number 2, number 3, and so on, each represent one person's data. So that's one participant or one observation, as it's also called. And importantly, when you're hunting around your computer, you should be looking for files that end in SAV. That's how SPSS saves data files, as opposed to different other types of files that we'll look at also, namely syntax files and output files. So those are different. But, you know, generally speaking, what you would do is either enter data in by hand, or, as I did, download data from a source that is either, you know, maybe an organization that you're working with, or perhaps a national database. It really depends on the specific question. So that would be really the very, very first step. And now this, so in tomorrow's presentation, this is where I would actually technically go in and do that, but we won't have enough time to get through the whole presentation if I were to do that. So for now, just stay tuned, I guess. In any case, at this point, once you have your data entered, you know, it might be tempting to just kind of run the regression on the data that you have and, you know, get that all-powerful p-value, right? But as we'll see, that would be a mistake. And again, I'll go into the details more tomorrow. Suffice it to say that you might find that there are real sort of problems with the data that you would not be able to detect without actually going in and doing all these diagnostic checks before you do a final analysis. And again, I'll demonstrate this tomorrow. Okay, so another issue with SPSS after you've entered data is when you go to do any kind of analysis, whether it's looking at, you know, the mean of a certain variable or trying to run an actual multiple regression, you have 2 ways to do it. One way is to just, you know, go to, you know, analyze, and there's a menu always that is sort of the heart of SPSS, where you go to analyze and then do any kind of analysis that you want. And then once you input, excuse me, once you input all the information that you want SPSS to give you, you can either just hit OK, and that's fine. That will run the command. But it has poor retention. It has a really bad memory. If you close SPSS, it forgets what you did. It doesn't save any of the options that you selected. It doesn't remember which data set you were working with. And it certainly doesn't remember what you wanted to do in the first place. So the alternative is to use syntax, which is what you see a screenshot of on the screen here. And what syntax does is it retains all the instructions, all the steps that you took during your analysis. So again, whether you're trying to just get a mean of a sample and maybe a standard deviation, or whether you want to run an entire regression command, whoops, which is what we're literally looking at here. All these lines here are just a regression command. You would be able to save this document. It's basically like a text file that SPSS understands, and you could run the syntax over and over and over again and get the same exact results without any ambiguity as to whether or not you're doing the same analysis, whether you forgot to check one of those little boxes that SPSS gives you. And furthermore, you could also send a syntax file and a data file to another person, whether it be a dissertation chair, a methodology expert, a colleague, what have you, and they would be able to exactly replicate your analysis as well and maybe troubleshoot some issues that might be inherent in the analysis, which they would not be able to do if all they had was perhaps an F ratio that you sent them or a correlation coefficient that you sent them. And what's nice about this also is that when SPSS goes to syntax mode, if you will, when you hit paste instead of OK to run an analysis, you still have the option. This green sort of play or go button is the exact same thing as hitting OK. And it's a really nice feature because you don't lose anything. You can still hit OK as long as you select, as long as you place the cursor in the right place on the screen, you can just go ahead and run your analysis and still retain the entire syntax file and annotate it. And annotating a syntax file is also very important because this, I'm sure that this looks like gibberish. All these different pieces of information, they make sense to me and maybe a few other people out there, but overall what you can do is you can write in what it is that you're doing. You'll notice here that I've typed in a little bit of text here, preliminary regression to obtain residual diagnostics. And then I know everything after that pertains to that piece of information. And so now when I come back to this later, after I've gone and taken an exam, after I've gone to see a client, this and that, the other, I still have an ability to know what it is that I did. So that's what annotating text is all about. And finally, as before, I mentioned that there's a different type of file for saving data, which is an SAV file. So an SPS file is where you can find syntax files. So just like a Word document, ends in DOC, PowerPoint ends in .ppt, a syntax file ends in SPS. Okay, so then now that we kind of have a little bit of an overview of that piece of information, and again, I'll be doing a lot of hands-on application of this principle tomorrow, but for now I think we can move forward and actually look at some of the ideas behind doing these sort of preliminary data screenings before moving on to an actual final analysis. So the very first thing that you would do is do a sort of rudimentary run-through of the data looking for out-of-range values. So this is particularly important if you have something like hand-coded data. If you have 100 participants who all filled out paper versions of a 20-item questionnaire, it's inevitable that you're going to make a mistake here and there. And sometimes that mistake boils down to a value that does not fit into the range of possible answer choices. So if you have a Likert scale from 1 to 5, for example, and you catch a couple of 6s in there, that would be really meaningful information which might otherwise skew the results. So this kind of rudimentary diagnostic analysis is always the very first thing you want to do, in addition to, of course, being very careful if you're entering data by hand. And then once you do that, then you can run a preliminary multiple regression model. And again, keep in mind, this is only specific to multiple regression. We're not talking about any kind of data screening for the second bullet point, that is specific to anything except multiple regression. This first point about rudimentary diagnostics, yes, this is for any kind of analysis, but for multiple regression specifically, this is where you would run a preliminary multiple regression model, plug in your now valid data, and look for information that is given by the data that SPSS outputs. So there are a few main ideas behind this, one of which is how the model actually performs. Another piece of very important information is the residuals, and I'll talk about those in a minute. And then, of course, if there are multivariate outliers that are also influential, and those would be also something I'll talk about in a little bit. But those are the first three important pieces of information that come out of this preliminary multiple regression model that tells you how well the model behaves, how well it's able to predict the outcome. Again, in this case, that would be the number of health professional visits. Once you've done that, then you can start to look at bivariate relationships. In a multiple regression framework, you have not only relationships between the predictors and the outcome, you also have relationships between each individual predictor and the outcome, and each predictor with all the other predictors. So you always want to inspect those bivariate relationships and ensure that those are actually linear and they don't follow really sort of funky trends when you make a scatter plot. And again, we'll see this in detail tomorrow, but when you look at the relationships between those variables, one of the main features of multiple regression is that it relies on linear relationships, not curvilinear relationships, and certainly not variables that are susceptible to being skewed by outliers. So you always want to look for those. And then finally, what you would do is look at the individual variables themselves and look at whether they're distributed normally and whether they themselves also have any outliers. So basically, what I want to do is today just take a conceptual look at each one of these 4 different steps, and then tomorrow dig into just the really sort of technical details of what each one of these 4 major steps would look like. So to start out, let's look at out of range values. Like I mentioned, this is something that you would do in SPSS and simply find extreme outliers. And these values would alert you to any kind of cases that have values that are outside the possible range, and then you can go look at those specific cases and find out what happened. If you had, maybe you meant to code a 1, but you typed in an 11, you could figure that out. If it turns out that there's a negative value where there shouldn't be, you could also find that out, things of this sort. So for now, we can leave it at that, and then what you would end up with is a data set with hopefully valid information. Obviously, if a variable has a range from 1 to 5, and you miscoded a 3 as a 4, without checking again by hand or checking a random subset of the data points, you really wouldn't be able to do much about it. So it's always important to be careful as well. So that's what we would do. Now, next up, after you would do that, again, like I said, you would have to do that preliminary multiple regression model, which really depends on the accuracy of the model is dependent on the way that the residuals look. And so the residuals is what really becomes the heart of the analysis at this point. A residual is basically the difference between the value that a model predicts and the value that's actually observed in the data on which the model itself is based. So the model is based on data, and then it makes certain predictions about what the outcome should be for any given data point given a set of predictors. It makes a best guess, and then a residual is what compares that best guess for each data point to the actual value that is observed on the outlier for that combination, for that specific observation. And essentially what you have is this relationship that each observation, i.e. each participant, has a residual. And each observation is based on all predictor variables. So you basically take all of those predictor variables and the model comes up with a best guess and then compares that best guess to the actual outcome that was observed in the data. So essentially, if you have a large residual, it means that the model is unable to predict an observation really well. So residuals are really kind of the canary in the coal mine that is signaling that something is not right about the model. And so tomorrow we'll look at a very specific way of looking at residuals, and we'll look at scatter plots, we'll look at multiple different ways of evaluating how well a model is able to predict an outcome. So that's where these next couple of steps come in. We know a little bit about residuals now, and so the next step would be to look at these other four questions. Are there multivariate outliers? Are there influential cases, which is a distinct concept from multivariate outliers? And then the second two pieces are multicollinearity and heteroscedasticity. And I dare you to say that last one 3 times fast. So what I want to point out also is that the first two questions have to do with each individual observation. So tomorrow we'll be looking at all the different cases and whether or not they can be classified as influential outliers. And the second two questions have to do with just the variables themselves and the way the overall model works. So they're kind of two levels of analysis, right? One is at the individual observation level, one is at the model level. I'm sorry, two are at the observation level and two are at the model level. So it would be nice to say that all these questions would be answered, that there are no problems, but that's never ever the case in the real world. There are always going to be violations, so we're always going to have to sort of move forward into the bivariate relationships and the univariate relationships that you see down at the bottom of the screen. But for now, I just want to focus on these first two, and then we'll kind of take it piece by piece. So when it comes to multivariate outliers and influential cases, there are a number of things to consider, but these things are still going to be a little bit dependent on the residuals themselves. So let's look at those in a bit more detail first. If we had looked at the SPSS output in detail, we would see that the model does perform relatively poorly, and that there are a lot of spread out residuals, so values that are too large to just ignore. And the question that begs is, of course, what is causing that poor prediction? And so this is where we start to look at multivariate outliers and influential cases. And by the way, if I'm talking a little fast, I tend to get excited about these things. And if you have any questions, just stop me, and Dr. Adu can, of course, also chime in at any point and ask questions if you want to type those in, or if you just want to speak out, then that's perfectly fine at any point. So the idea is, what could be causing the model to be not very well able to predict outcomes? And one of the possible answers is that you have multivariate outliers. And a multivariate outlier is typically found by the Mahalanobis distance. And this is a measure of the distance between one particular case and the mean of the predictor variables, which is also called a centroid. So no matter how many predictor variables you have, they have a sort of multidimensional center, and the distance of a observation from that center is what the Mahalanobis distance tells us. So with our specific research question, we have 3 predictors. And these 3 predictors dictate that we find a critical value above which the Mahalanobis distance is deemed to be a multivariate outlier. And with 3 predictors, we end up finding that value is 16.266. We'll look at the technical aspects of that tomorrow. But basically, any value above that critical value would be sort of flagged as a potential problematic case. So you can sort the data by the Mahalanobis distance and look at which cases could be leading to any kind of problems with the model. Another aspect of individual data points is whether a case or an observation is in fact influential. And there are two ways to look at this. One is to look at a measure called DF fit, and this is a measure of how much an outlier a case would actually be if the regression were first run without that data point in it, and then later, if that data point was added, how much it would deviate from the line of best fit. And the other option is to look at it kind of in an inverse way, and that's the DF beta, which is a measure of how much the regression line would change if a case were omitted. So you look at the regression line with the case and without the case and compare how much that would change. And so both of these are useful in their own way. The ideal thing is to use standardized forms of DF fit and DF beta, and I'll talk a little bit more about that in detail tomorrow. For now, suffice it to say that there's a good rule of thumb that values between -1 and +1 are okay on DF fit and DF beta. Any values outside of that are not. And again, if they're outside of that range, if any case is outside of that range, then again, you should flag it, just like you would any case with a large Mahalanobis distance. Okay, so what is it about influential cases, right? How can we distinguish between a multivariate outlier and an influential case? Are they the same thing? Are they not? They are not. Although often they, in theory they're not, but oftentimes they end up being related. So here's an example of some data that also came from the internet. This is murder rate plotted against violent crime in 50 states. And so you can see there's a pretty good linear relationship here. The higher the murder rate, the higher the violent crime rate. Seems to make intuitive sense, right? What we might have, though, is the following data point. Something that is way high on murder rate. And this is actually data from Washington, D.C. So you have a lot of murders and you also have a lot of violent crime. But what you'll notice if you switch back and forth, if this data point didn't exist, that line of best fit isn't moving a lot at all, right? So yes, it's an outlier, but no, it's not influential. On the other hand, what if there were a lot of murders in DC but not a lot of violent crime? Now you can see that that line of best fit is really sort of tilting away from what it would be with an uninfluential outlier. So now we would call this an influential outlier. And so these DF beta and DF fit statistics will tell us for every single data point how big of a change in that line would be caused by either adding that point in or leaving it out. So the take-home point with all of this is sort of a really good quote that, I want to share with you, which is that if a point is a significant outlier, whether it's multivariate or univariate, but its influence is low, then there is no real need to delete that point since it does not have a large effect on the regression analysis. However, one should still be interested in studying such points further to understand why they did not fit the model. So essentially what we want to do is make sure that we don't have one apple ruining the whole batch, but at the same time, we need to know if it actually is capable of ruining the batch, right? So you don't want to be throwing out data just because it's an outlier. You have to be sure that there's a good reason to throw it out, or if not, at the very least, you want to see why is it an outlier? Why is it influential? You can look at your data and try to make some inferences about what's going on with the data to try to guide subsequent analyses. Now, at this point, you could certainly take out any data points that are multivariate outliers and or influential outliers and rerun the preliminary regression model. But we're not going to do that. In the case of our data, that would be a waste of time. Just a bit of a spoiler alert there. What we do have is the opportunity to keep looking, keep digging deeper into the data and seeing what else could be happening. So let's look at these questions of multicollinearity and heteroscedasticity. And again, these are moving a level above observation, individual observations, and looking at how variables interact with each other and with the model itself. So the first question is of multicollinearity. Multicollinearity is when two predictors are highly correlated with each other. So basically you're looking for Pearson's correlation coefficients greater than 0.8 or 0.9. Depends which expert you ask. They will tell you that either 0.8 or 0.9 is the minimum cutoff, at which point you should start worrying. If it's greater than 0.9, certainly that's a cause for concern. The problem with highly correlated predictors is that it leads to larger variability in estimates of beta coefficients. Beta coefficients are basically correlation coefficients. So with a beta coefficient, you can essentially say for every 1 unit increase in a predictor, what is the concomitant increase in the outcome? And if you have correlated predictors, then you can't really figure out that well, not you, but the model can't really figure out which of them should be used to make that estimate of the effect size. So that becomes problematic, and the estimates start to be much more unpredictable. And also, collinear variables tend to explain the same variance in the outcome, and they explain it equally well if they're highly correlated. So the question becomes, well, which one is more important? If you have two variables explaining the same variability in the outcome, some way, somehow, you have to come to grips with the fact that they're basically confounds. And that will boil down to having to either pick one or giving one of them priority over the other, and then making theoretical judgments about which is more important, which one should be entered into the model first, so on and so forth. Again, we'll look at that in a bit more detail tomorrow. Okay, so the way that multicollinearity can be examined is first by looking at the correlation matrix. A correlation matrix is basically looking at the correlation coefficients, Pearson's R, between every combination of two variables. And if any of those are greater than 0.8, you can start to flag one of those variables as potentially needing to be taken out or given lower priority in the model. And right, so that's what these two pieces of information at the bottom are. You can either eliminate one of the variables or use stepwise multiple regression to determine which variable to eliminate, or in fact which variable to give precedence. So that's not there in black and white, but that's what it can be used for. So that's what we will be doing tomorrow. For now, again, more conceptual. So multicollinearity is also important in terms of this variable called tolerance, which is part of the regression that we ran at the, that we will have ran at the beginning. And you're looking for tolerance values less than 0.1. And what's interesting about this is that the tolerance is the amount of variance not shared with any other predictors. So you look at the tolerance for each predictor and see how much unique variance it can actually account for. And if it can account for a very small amount of variance on its own, is it really that useful? Especially if it's collinear with another variable. If it is, then it's not adding very much to our interpretation, and in fact, it might be hurting the model by making our ability to predict the outcome much more, unpredictable. So we have to watch out for this this variable of tolerance. And right, if this criterion, if the tolerance value is less than 0.1, then the variable should be removed from analysis because it's not adding anything, and in fact, it's hurting the analysis. So tomorrow we'll be looking at specific collinearity diagnostics for the data set that we're going to be working with. Okay. So now the next question is, are there any other measures of multicollinearity? And the answer is yes. There is one more measure, and it's called the variance proportion. And essentially what we're looking for here is the individual predictors to essentially load onto unique dimensions that SPSS generates. So what you don't want is multiple factors to be accounting for a lot of the same variance. And the idea is that if they are, then you really have to, again, start thinking about whether or not you want to throw one of those variables out. One of the other necessary conditions for this, though, is this condition index that has to be greater than 30. So if you have a condition index greater than 30 and two variables loading onto the same dimension at a rate of more than 0.5, or again 50% of variance in the outcome, then you want to seriously consider removing one of them, either on theoretical grounds or on statistical grounds, whichever one, for example, is loading more onto that factor. Or I'm sorry, that dimension. Okay, and that does it for multicollinearity. So some criteria there. The next thing would be this notion of heteroscedasticity. Now, what we're doing here is we're coming back to the residuals. So let's start with a sort of textbook example of a lack of heteroscedasticity, which is homoscedasticity. And the definition of homoscedasticity is the variability of residuals is approximately the same across levels of the predicted values. So essentially what that boils down to is if you have the predicted values on the x-axis, right, what you want to see is that at high values you have the same amount of error in prediction from from up and down as at the lower end. You want to see the same amount of variability in those residuals, right? And in the middle as well, everywhere across. And so that's why you may have heard that residual plots should be this sort of cloud of data. What we often find in real life data sets is that it's never as clean as that. Heteroscedasticity comes in a few different forms, a lot of which are often also combined. So sometimes you'll see that there are a lot of values on one side of the residual plot and really bunched up on the other. This is where a lot of analyses require transforming their variables. The same thing happens with this kind of funnel shape down here in the bottom right. As you can see, there are very small residuals on one end, but very large residuals on the other end. So if the regression model is trying to draw a line through this, that line could go this high, or it could look like this, or it could look like this, and it just becomes very difficult to try to take whatever estimate it comes up with at face value. So what our goal is going to become is making the residual plot as normal as possible, i.e. this top left form of it. So okay, it comes in a few different forms, and the rule of thumb is when you're looking at a residual plot, you would say that you have heteroscedasticity if the largest residual is 3 times greater than the smallest residual. That's a good rule of thumb. Now, that's not to say that that's something that you should go by, as gospel or anything. If you see a scat plot that looks like any one of these 3, you know that there's an issue going on. So there's really no reason to rely solely on that rule of thumb. It's just as important to look at the numbers as it is to look at the scatter plots and later on histograms. So basically, once we establish that there is heteroscedasticity, if we establish that, which in most cases ends up being the case, unfortunately, then we start looking at the bivariate relationships. So the linear relationships among all variable pairs and looking for any bivariate outliers as well. So when you have a correlation of a scatter plot, we looked at this this notion of let's see, where is it? The murder rate versus the violent crime rate. Then we can start to look at scatter plots in terms of just their bivariate nature. So this is a very rudimentary example, right? We have one variable measured on the x-axis, another variable measured on the y-axis, and then looking for any outliers that may be in the scatter plot. And what that ends up building towards is, just because it's an outlier on this scatter plot does not necessarily mean that it would be a an outlier in a multivariate analysis, where you have basically multiple dimensions along which each case can be an outlier. But it is, once we get to this point and we're dealing with all these different problems, it is likely that getting rid of these outliers or transforming the variables would in fact provide us with a solution to some of these problems, i.e. making the residuals plot more able to predict outcomes. So the way that we would look at that is using the same techniques as in multiple regression, except now there's only one predictor instead of multiple predictors. So again, you can look at the Mahalanobis distances, and now the critical value is lowered because there's only one predictor. And you can also use those DF fit and DF beta statistics to identify influential cases. And you can also do visual inspection of the bivariate scatter plots, like I just did by scrolling through and looking for any data points that look like they kind of jump out at you as being outliers. And we'll, of course, again, go into this with a detailed example tomorrow. Okay, and then once you've done that, and there are still problems, then we start to look at the individual variables themselves. And here we're looking for normality of distributions and any univariate outliers. So basically anything that's in the tails of the distribution. So individual variable distributions. Do we have normal distributions of all the variables? And this has to do not only with the predictor variables, but also the outcome. Excuse me, I think I might sneeze. Okay, so what we ask SPSS for is the mean, the standard deviation, the skewness, the kurtosis, and to save standardized values. The standardized values will give us z-scores, and z-scores are what we use to identify what percentage of our data is either on the upper end of the distribution or the lower end of the distribution. Pardon my chicken scratch there. And so what we would also do is look at an actual statistical test of normality of these distributions. And you'll notice there's an asterisk here, and that basically means that I shouldn't forget to mention this, because it's not necessary for each individual variable to be normally distributed for multiple regression. I repeat that, not for other types of analysis, but for multiple regression, you don't need each of your variables to be normally distributed. Only that residuals plot has to be normally distributed. So you can run these tests of normality, but even if they are significant, it's not necessarily a cause for concern. It's just to check and make sure that there's, that there are or are not violations, and then you can move forward from there. Okay, so basically we would ask SPSS for all those different statistics, and then we can start to look at where along the sort of hierarchy our biggest violations were. Is it those multivariate outliers? Is it the influential multivariate outliers? Is it bivariate outliers? Is it non-linear relationships between variables? Is it univariate non-normality. All these different things could be the cause. So now what we have to do is start working our way back up. So we start again at the bottom. What we would do is we would look at our univariate distributions and see what they look like. A lot of the time what we end up having to do is transform variables. What transforming a variable is taking the raw scores and multiplying all of them by the same factor, which can influence them disproportionately. One of the most popular ways to do this is with the log transformation, as it's called. And this is applicable to positively skewed variables, meaning variables that have all their data bunched up at the lower end of the distribution and then a few really high scores pulling the mean and creating outliers. And what a log transformation does is it scrunches those outliers closer to the center of the distribution. And a square root transformation is also very similar. And sometimes you can consider both and decide which one literally makes the distribution look better. And that's for positively skewed variables. Now, there are also negatively skewed variables. When you have a negatively skewed variable, it's the opposite. All of your data points are sort of bunching up towards the higher end of whatever scale you're analyzing. And there's a few out in the lower tail that are, dragging it, not dragging it, that are, outliers in a sense from the relatively high mean value. So what you would have to do for negatively skewed variables is do what's called reflect the variable. And essentially what that means is you just take the largest score of your data set on that variable, add 1 to it, and then subtract every single observation from that largest score plus 1. And that will basically take that distribution, flip it, so that your tail, whereas it was on one end, now it's on the other. And then once you've done that, then you would transform it just as you would a positively skewed variable like I described above. And then you can re-reflect it to get back to the original interpretation for when you're actually running your statistics. Hopefully that makes sense, because if you didn't re-reflect the variable and then you saw a negative relationship between your reflected variable and the outcome, you might make the opposite inference that you should. So it's always important to make sure that this does not trip people up. Okay, so if you have more severe skew, whether it's positive or negative, doesn't really matter. There are more options for doing transformations which are beyond the scope of this presentation. We could do something like a reciprocal transformation or use like a Poisson regression. These are all really more sophisticated topics that we would focus on in like a methodology consultation. But for the general audience, you have some options if your variables violate normality visibly and statistically. Now again, I stress that normality of individual variables is not necessary for multiple regression, but the normality of the residual plot is required. And what happens a lot of the time is that the non-normally distributed individual variables are the culprits. So what you would end up doing is transforming the variables, rerunning the same regression with the transformed variables in place, as opposed to the raw variables that we used for the first regression. And then you would conduct a normality test not on the the raw variable on the transformed variables themselves, but on the new residuals. And so a Kolmogorov-Smirnov test is how you would do that. This will tell you, in addition to looking at the scatter plot of the residuals, it will also tell you, statistically speaking, whether or not that distribution of the residuals violates the normality assumption. And at this point, you can trust it. So we'll look at this again tomorrow, so stay tuned. But now at this point is when you would do your final analysis. And I'm going to gloss over this right now, but basically what I have on the screen here is 3 different regression analyses, the first of which is using just raw, unaltered data, the second of which is data that have been sort of screened. And then the third one is for the fully transformed trustworthy model. And each of them has different findings. What I'm just going to sort of point out for those who want to, zoom in on this and pause it for now, we'll look at it in more detail tomorrow. Have a look at the standardized beta coefficients for all of, whoops, I didn't want to cross that number out for you. Sorry about that. Look at this column, the standardized beta coefficients, and look at the significance values of those coefficients, and also look at the 95% confidence intervals. And the width of these confidence intervals is also going to be very important, because this is how confident we can be in the estimate of the coefficient itself. So with that, I'm going to go to the next slide, and we'll look at this again in more detail tomorrow. Keep in mind that for this analysis that I just kind of will have gone through, all the variables were positively skewed. Now, we didn't see this. We'll see this tomorrow. And the multivariate normality was achieved. There was no missing data. It was a relatively large data set, and all the variables were entered in one step. All the predictor variables were entered in one step. So each one of these points could have gone in any one of a number of different directions. And had that happened, then there would be many, many different types of remediations that we could do. And on top of that, there are also many, many more different types of analyses, whether you have categorical predictors and categorical outcomes, whether you have categorical predictors and continuous outcomes. There's all different kinds. So when it comes to things like that, that's where we recommend meeting with a methodology expert at NCAID and really getting down to the fine details of your specific analysis. So make sure to reach out to us if you find yourself stuck somewhere along the way. And with that, I want to thank you for your attention and see if there are any questions.